Thank you, madam. The reason I'm doing this is because it's important how you draw it, and it takes practice. And I'm sure most of you can do it, but I'll just show you. If you can make something look a bit like the real thing, then it's great. Because if you haven't got the model, so if I draw a diamond, I always start with one above, one out one side, and then the others. So I'm drawing the tetrahedral arrangement. And then I go down from this, down from that, down from that, and then I join them here. And suddenly it starts to look a little bit like the model. It's not difficult to do. That took me no time, especially when you realize that each alternating layer has a different pattern. So the red layer in this layer here, it has one up and then three down. So here's one in the red layer. So red, green, red. Here's one, it has one up and it would have three down. I haven't bothered drawing all of them. The green layer is the other way up. So it has one, it's like upside down. So instead of being like this, it's like this. So this one here, it has one there, and then it would have three like this, one down, three up. Okay, so you can just draw a bit of it. And the students like this because they can practice doing it. They can understand this. They go, hey, it's really strong. Why is it really strong? Well, this carbon has 4 bonds, and we know covalent bonds are really strong. 4 bonds, to break 4 bonds for every single carbon, very difficult. Then you can draw graphite. So graphite is in layers, okay? Weird layers with gaps between them, which make them able to shift across. But each one of the layers is hexagons. Why can we see through diamond? We can see through diamond because although when I hold it like this, it doesn't look like there are holes in it. When I hold it like this, you can see it's hexagons. It's hexagons with holes in them. Look, I can see straight through it. Light can get through it. This one, it is hexagons, but the hexagons are not lined up. So in this layer, in this top layer, the next layer is arranged so the atoms in this one are in the gaps of this one. So the light can't get through. So your pencil doesn't let light through, not unless you have a very expensive pencil made of diamond. So in that, then I just draw, okay, I say, let's draw hexagons a little bit flat. So I've drawn a hexagon and I've just turned it slightly flat. Then I draw more. It doesn't matter how good they are. They don't have to be very good looking hexagons. You're just drawing some hexagons. And then you leave a gap and you draw another one. Okay, so there's another set of hexagons down here. I don't care that it is not actually directly above. That doesn't matter. The point is that I'm now saying this carbon here is joined to 1, 2, 3, and down here and up here is another one. So I have 1 bond and 1 bond and 1 bond and a sort of a half a bond and a half a bond. And that's why the layers can slip over each other and we can write. When we write with a pencil on a piece of paper, we are leaving layers of hexagons on the paper. And the students like that. They like to think maybe they can see the hexagons, which they can't. So learn to draw these sort of things because it will help you. It doesn't matter whether it's a blackboard, a whiteboard, on a piece of paper, it doesn't make any difference. If you can walk up to a kid and draw it on the student's book or on this, or like that thing which I showed you on my PowerPoint, if you're drawing on a tablet, you can often replay that thing on the tablet. Okay, you can often replay that little film so they can see you draw it. That is very valuable. Now, the point about this is I'm starting with covalent. I'm starting with giant covalent. But what I would normally do is to if I could do a practical, great. If I can't, it doesn't matter. I'm just going to go through the properties of ionic, covalent, and metallic, because many of the students can tell you what metals do. They won't be able to tell you lots of other things, but this is what I do. So I go, okay, let's look at the properties of metallic and ionic and covalent substances. And I say, all right, let's start with metallic, because metals, many of us know a metal, okay? So metallic chemicals, and then let's do with the ionic ones, and I'm going to do the covalent ones last. Now, there is a reason why I'm doing the covalent ones last, because you know there is simple covalent and giant covalent. There are things like water, wax, oxygen, nitrogen, carbon dioxide, sugar, and then there are giant ones like diamond and graphite. So I'm going to divide this up afterwards. So I said, okay, let's look at simple stuff. Let's look at the melting point and the boiling point of metals. Now, if you have the ability to, what I would normally do here is I would give them a table with some metals in, some ionic things in, some covalent things in, with their melting point, with their boiling point, and so on, so they can observe them, so they can look at them, they can look it up themselves. If you remember, I said at the beginning, my teacher, as a teacher, I mean, teaching me to be a teacher, had said I shouldn't talk for more than 8 minutes, and I believe you should make them work. You should make them do the work. So if you can get a table or write on the board, you get some data and you write down the melting point. Okay, sodium chloride, melting point, 801 degrees Celsius. You know, you write down a whole load of these things, then they can look at this themselves. So the point is that many of them will know that the melting point and boiling point of metals must be high. They know it must be high because the exhaust on the bus does not melt. They know that I don't know, whatever it is, you know, the rocket does not catch fire. Well, sometimes it does. The rockets, when they see them go up, they do not catch fire. They should not catch fire, right? They don't catch fire because they're made of metal and they don't melt. Okay, good, excellent. If you have given them some information, sodium chloride, melting point, 801 degrees Celsius. Why do I remember that? Because it's useful. This is very high. But from your table, they will find 2 kinds of covalent substance. They will find things like water, which ice melts at 0 degrees Celsius. Nitrogen boils at minus 196 degrees Celsius. Diamond does not even melt for 3,500 degrees Celsius. So then you say, okay, there are 2 different kinds of covalent. So to start with, I'm going to just call them covalent 1 and covalent 2. So I'm not going to go into molecular forces and so on to start with. I'm going to say there seem to be 2 different kinds of chemicals which are covalent. So some are low and some are high. Okay? Then I say, okay, let's look at their solubility in water. Metallic. If you want to make your speedboat out of aluminium, you better hope it is not soluble in water. Metals do not dissolve in water. Ionic things, some do, some don't. Some do. So, sodium chloride, but some don't. Bauxite, the ore for aluminium. Aluminium oxide, we get aluminium oxide out of it. It doesn't dissolve in water. So that's not a very useful box. Covalent, A lot of those with low melting points do, but the big ones, the ones with high melting points, they don't. So then we look at some of the examples, because the examples are useful. So I say metals, we know metals, iron, copper, silver, gold, aluminium, they all know those. Ionic, I give them examples, salt. They always then say, oh, sugar? No, 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 no. Sugar is one of these with low melting point, and solubility of water is yes, okay? Then I look at conduction of electricity. And they go metals, yeah, metals do, because I know they are in the cable, they're in wires. I know that they conduct, yes, they do. Easy. Ionic things, if you are lucky enough to have a laboratory where you can show them, build a simple circuit, build a really, really simple circuit with a bulb in it, and put your element in the circuit and see if it conducts electricity. Does the bulb light up? And the fact is that if you take ionic substance, it doesn't. It doesn't when it's solid, but it does when it's liquid. And we can talk to them about why that happens. We talk about what is it that happens when metals conduct electricity? Oh, the electrons can flow through between the ions. So what is electricity? Well, electricity is the movement of charged particles. Charged particles, electrons, ions. These guys in ionic, only when they are liquid can the ions move. And if the ions can move, they can conduct the electricity. That's the point. When they are stuck in a solid, they are in fixed position. This is a model. No, this is a better one. This is a model of sodium chloride, right? Sodium chloride, repeating unit. Each sodium has 1, 2, 3, 4, and one in front and one behind. Each chloride has 1, 2, 3, 4, one in front, one behind. This is called a coordination number of 6, 6. The point about it is this, that all of these ions in the normal solid will be vibrating. Okay, they'll just be like this, but they can't move around. When I melt it, it comes to pieces, then the ions can move. And if they can move, they can conduct the charge. These guys cannot. These guys, all the electrons are in the bonds in this. They're all stuck in here. So for what we call giant covalent, for most of them, all of the electrons are used up in the bonding. So in other words, the ones with very high melting point and boiling point usually don't. But there's this stuff called graphite, which is annoying because it contradicts, because these weak forces between the layers, which don't hold them very strongly, the electrons can move through between the layers. So they can't conduct in this direction, that way, but they can in that direction. So graphite can only conduct a bit. It's not a great conductor, but it's important that it is. The simple covalent ones cannot, unless the power gets really, really high. Now, the idea that we've got to get across is the difference between these guys, covalent 1 and covalent 2, and the fact that the covalent 1 are tiny little bits and pieces which are not very interested in each other. And this is a place where you would normally draw diagrams and so on. So the giant ones are really easy. We can talk about this, we can draw it, we can say, you can see this. I mean, If this was a real diamond, and these were real atoms, in other words, the size of real atoms, I would not be able to see it, even with a really powerful microscope. Okay, to see a diamond, we are talking about billions and billions and billions and billions of atoms. So this would be invisible. And they don't get that. But if you said, well, I need to fill the whole room with a model like this for you to be able to see it, then they say, ah, now I understand giant. This piece of salt would not be visible, even with a really powerful microscope. We would need billions and billions and billions and billions. We would have to fill the room with yellow and green beads to make it the size of a salt grain. The students need to understand the size of things. So what do we do about intermolecular forces? So we have to explain why this is true. And this is a place where we would normally draw diagrams. Oh, before I move on, sometimes what they do is this. Whoops. Okay, here are some chemicals. We are going to call them R, S, T, and U. R, S, T, U are not their normal formulas. And I'm telling you that R has a high melting point. It doesn't dissolve in water. It does conduct electricity all the time. And they give me a list of chemicals. So let's say my chemicals, let's say I have aluminium. I'm going to have magnesium chloride. I'm going to have carbon dioxide, and I'm going to have graphite. And I'm going to be specific. So I'm going to say, there. So what the students now have to do is they have to choose which is R, S, T, and U. And you go, okay, this is it. The only type which always conducts electricity is a metal. Okay. S, high melting point, boiling point, dissolves in water, don't know, conduct electricity. It doesn't conduct when it's solid. I know that's ionic. Ionic. Which one of these is ionic? Ask Mick. Mick said I is metal, non-metal. I know graphite is a giant structure. I know it will have a high melting point, boiling point. So it must be. That's it. That's how it works. Okay, that's a simple question. If they can learn this table, they will be able to apply it. But it takes a while. You have to go through. I would go periodic table, electron configuration, arrangement, electrons in outermost shells, unreactivity of noble gases, and therefore everything wanting to be like a noble gas, so gaining or losing electrons. Then the difficulty, sometimes they can gain and lose, and sometimes they have to share. Before I forget, there is something which my students found useful, and it's this. They are used to this in maths, I suspect, as a Venn diagram. One girl in one of my sets said, I know how to remember which one is this, because The V told her. She was used to maths, which was overlaps in sets, and she came up with covalent. It's the V which tells me that. So last little bit, intermolecular forces. And then I will show you a revolting. How much longer have we got? Have we only got 20 minutes? Well, I will hang on afterwards anyway, but I'm going to show you a revolting experiment to finish with because it's quite fun to do. And it's quite fun for you to be able to see it, I think. So I will finish with a revolting experiment.
You've got 20 minutes, Mark.
That's okay. That's loads, man. Thanks, mate. But intermolecular forces are really important. And the idea is this, because students get a bit confused by this. But if I say, okay, water, it freezes quite easily, not without a freezer, but it freezes quite easily and it boils quite easily. And the students have to understand the graphs which look like this. If I start at, let's say, -40, and I go up past 0, there's 40, 80, there's 100. This is temperature in degrees Celsius. This is time along the bottom. And I start with a beaker with some ice that I've just got out of a really, really cold freezer at -40, and I start heating it. The temperature goes up, then it goes across, then it goes up, it goes across, goes up. And we know that what is happening is that in this bit here, this is only ice. This bit here, the ice is melting. This bit here, between here and there, this is water. This bit, oh, sorry, that's a bit too far across, doesn't matter. This bit is boiling, and that is steam. Okay, beyond. So what they need to understand is that what is happening here is I am still heating, but the energy is going somewhere else. And the energy is not going into raising the temperature. If I took a bar of metal and I just heat it up and heat it up and heat it up, I would find the graph just went up, you know, just like straight up like that. But with ice, at -40 to start with, it goes up and then it goes across. And it goes across because that is the point where the particles are moving away from being the solid and starting to break away from the lattice, the irregular arrangement. So here, the particles are stuck together in a really regular sort of arrangement like this. Here they're starting to fall to pieces. Here they are still very close together, but they are now not organized. And then here they are really, really spread out. But in this bit here, the particle movement is starting to overcome the forces of attraction. What the students find difficult is to understand that this graph is the same for just about every substance on Earth, but the temperatures are different. So if instead of ice, I had salt, then all I do is I change these. And I go, okay, this is not ice, it's salt. And this is not water, but molten salt. And that is gaseous. That is gas, NaCl. And this number here is 801. And this number here is something like 1350. I can't remember. It doesn't matter. The pattern is exactly the same each time. These points here and here are disrupting forces. Okay? The particles are moving enough to get away from each other. If you do this with students in the room, we can get students to hold on to each other as the solid, okay? And we say, as we heat it up, what happens? So they start to move around like this. What happens when they melt? They move around enough so they get away from each other. You have to be careful because the behavior of the students can be poor. You have to be careful. So we can get them to start to move around and get away from each other a little bit, but they have to stay really close together. Then here, they are getting away completely. There is no attraction between them. So there are only two forces of two intermolecular forces which you have to know about for KCSE. Hey guys, you have been so patient. Well done. There are only two forces which you need to know about. For those of you who know quite a lot of chemistry, you know that's not true. You know there are more forces. But you are taught for the KCSE that there are van der Waals after a Dutch guy called Van der Waal and hydrogen bonding. And the easiest way to remember it is that hydrogen bonding is not often found. Not often found? Yes, because it is only with N, O, or F attached to H. So hydrogen bonding only happens with things like water, things like ammonia, things like hydrogen fluoride, things like the alkanol, ethanol, things like higher up. This is what we call an amine. It doesn't matter. Anytime we've got H directly attached to one of these guys, there, here, when it's directly attached, it is so polar. And what polarity is an unequal sharing of electrons. So the oxygen is better at pulling electrons towards it than the hydrogen. So the oxygen becomes a little bit minus. That becomes a little bit plus. The letter is the Greek letter for D, but it's the lower case. And that will then attract, here is another water, which just happened to be going past. Sorry, another ethanol, which happened to be going past. And they are attracted because this is delta minus and that is delta plus. Most other things like carbon dioxide, oxygen, nitrogen, they have lower melting points and boiling points because they do not have this. And what nitrogen relies on is van der Waals. And so van der Waals happen because of something really odd. This is the bonding in nitrogen. And most of the time, these pairs of electrons do this. But some of the times they get it wrong. And they're suddenly all over here. And then this, for a moment, is minus, and that is plus. And that affects the next nitrogen. And then they attract each other. That is what van der Waals forces are. We call them dispersion forces, or induced dipole, which you may need. You may know, but that's what it is. So I'm going to finish with asking a couple of questions. Right. Okay. I know that's a bit rushed, and I know that you will go, well, I still don't know how to teach structure and bonding. If you have a chance to look back over this, or if you start to think about how you would structure it so you are going back to what you didn't understand, go back to outer shells, bonding, give and take, because it's much more obvious with ionic than with covalent, then metallic, then give them the shape of the table with the properties and look at them. So why is a piece of metal so strong? Well, it's strong because all of those ions in here, which are in a lattice, and all the electrons hold on to each other. How come water moves around? Well, because the hydrogen bonds are sort of okay, they hold them together in there, but at this temperature, there's no way that they can hold them together to form this. So I can build out of this, I can't build out of that. And when it comes to gas, how useless. But that's only about that temperature, because as I showed you with that graph, which goes like this, it's all about the temperature. So I thought I'd show you, I'm going to show you two things. I'm going to just change my camera. I'm going to show you two things because they're, oh, hello, what's happened there? My camera's just turned off. I'm just turning it back on. I hope it's going back on. Okay, for this one, I'm going to just go back to something which I did right at the beginning with the orange tablet. Okay, let me just turn that around. I can see what you can see. Okay, here's the orange tablet, and I'm going to do something silly. This is something which you can do, which entertains students. Every time I do lessons, I always try to have something that I can show them, which is a bit unusual. I'm going to put this up a little bit. Yeah. Okay, what I'm going to do is, this is a film canister, just one of those old-fashioned plastic film canister with a top. I'm going to put a small amount of water in it. Just a little bit of water in it. And I'm going to drop the tablet in it. And then I'm going to put the top on and I'm going to turn it upside down. And we'll see what happens. I'm going to do it over here. I hope you can see that. Yes. If you remember, the room is quite big. There's the ceiling. It's quite a big room. Okay. So here we are. So tablet, water, little watch it, put it in, put the top on. I've turned it upside down. Nothing seems to be happening. Oh dear. Okay. That went up and hit the ceiling twice because it came down, hit one of the bins, went up, and then it came down. So it shows the power of gas. The point being, we had a solid and a liquid, and the particles were moving hardly at all. Then we produce a gas, and the gas starts to move around so much, it produces a lot of pressure. Let's go over to the fume cupboard. The last one that I want to show you is over here. I'm going to make it a lot closer, hopefully. Okay. This is a piece of chemistry which they need to know for Form 4. No, Form 3. I have here some sugar. I just do it because it's quite an interesting experiment. I'm going to add a little bit of water because it's going to speed it up, but the water isn't really part of it. Okay, so I've got basically just some wet sugar in here. Now I'm going to add some, I hope you can see that, concentrated sulfuric acid. I'm going to give it a little stir. And now I'm going to leave it. And we'll see if anything happens. Let's get a little bit closer. Okay, so you can see the top of the beaker, but not much else. Oh dear. Okay, something is happening now. This is the sugar and the concentrated sulfuric acid reacting to form something pretty revolting. It seems to be coming out. There seems to be smoke coming out of it. This is good. This is a very, very peculiar chemical. I'm just putting some gloves on so I can show you something afterwards. Stay up. Stay up. Getting quite big now. It doesn't want to stay in there. It's pretty big. Oh dear. What we have is a large lump of carbon, which has been formed, and a lot of steam, and it smells like burnt sugar. Oh dear. Hello. It's pretty revolting. It doesn't want to stay. And this is because concentrated sulfuric acid is a dehydrating agent. And what we've got is a solid having the water taken out of it, or the elements of water taken out of it. That water then taking up much more space because it becomes steam, and the steam pushing the whole thing apart. We are left with carbon as a great big lump, quite solid. And the equation is this. This is solid. This is solid. This is a gas. And therefore the gas, the steam, pushes the carbon apart, which is why it gets so much bigger. And it's really quite easy to do, really not too difficult at all. And I hope you sort of quite enjoyed that and the exploding little bit of stuff there. Okay, so. All right. So that is the end of the session. I hope some of it was useful to some of you. I will stay here now. If anybody wants to stay and ask any questions, you can either put it in the whatever it's called, the
group chat.
What's it called?
Group chat.
The group chat. Okay, I can see. I will be able to see that. Okay. And I will stay if anybody wants to ask any questions. For instance, the person who didn't understand the potassium manganate and iron 2 calculation, if you want me to go through that again, I could. But any other general questions I can have a go at, and I will write answers as well. I honestly believe this, guys, that you have been extremely patient. It is quite difficult for us to judge where to set the standard and so on. And I'm sorry if the moles for some of you was a bit hard, but for some of you it's obviously really easy. I hope I didn't either talk down to you or make it too difficult. I hope I gave you some ideas. If you can use things like these, like the fold over game, like the go back to the ideas, make the ideas simple so the foundation is really good. So you go back to your own understanding and go, what was it that I didn't understand to start with? And remember, they should work harder than you. I know it takes planning, but it is much better to plan that they have activities, you don't talk too much, they have lots of things to do. I know that's not what I've done with you, for you, but that's because I'm trying to get a lot of information across in a short time. Moles, in one of the schools I looked at, was given 30 lessons. I did it in 2 hours. Structure and bonding was given 18 lessons. We've had an hour and a half. So we can't expect to cover it in the way that we would if we were doing absolutely everything perfectly and give you many examples. But I hope a little bit of it has been useful. And if it has, asante. And I will definitely be back if anybody wants me to do things like enthalpy, energy changes, and energy and electrolysis and so on, because they are hard to communicate. But in the meantime, I will say kwaheri, bye-bye, and good luck with the rest of your Saturday. So you should get out in the sunshine. Is it warmer now? Is it more than 16? Is it more like 30 or? What is it now?
Yes, thank you. It's 28 now.
Sorry, say again. And let me just turn this fan off.
Yeah. Asante sana, Teacher Mark.
Asante sana, headmistress.
We've enjoyed the lesson.
Well, if you learned any chemistry, headmistress, then you're a better person than I am. And if the head, I tell you what, teachers, I tell you what, one of the worst things is having the headmistress and the headmaster here watching you. It's terrible. When you have your lesson, make sure that the headmistress, headmaster, they're never there. Tell them, oh, no. Today we're not doing that lesson. Okay? So I will.
There is a question.
I'm going to look at
There is a question.
Yeah, I'm going to look at the chat. Oh, where is the question?
One of the teachers here.
Let me just get.
Okay, I'm Bernard and I'm teacher Bernard Makanda.
Hi, Ben.
Now we have said that ionic bond is formed between a metal and a non-metal.
Correct.
Right? Aluminium is a metal, chlorine is a non-metal. Why do they form covalent bond?
Okay, the truth is that bonding is a continuum from 100% covalent to nearly 100% ionic. Do you know the term electronegativity?
Get you.
Have you heard electronegativity?
Have you heard of it?
Yes, yeah.
Okay, then you will know electronegativity is the ability of an atom to pull a bonding pair of electrons towards itself. Let me just do it on the board briefly. So, if we look at the periodic table, here's the periodic table. The most electronegative elements are up here, fluorine at a 4, and the least down here. So electronegativity increases in that direction. Okay, so if we think about bonding as being a continuum, not like a spectrum, okay, like continuous, from 100% covalent to 100% ionic. And if we think, okay, at half and half, if it is just that side, it is ionic. If it's this side, it's covalent. Then what happens is this. If I look at two atoms, which have exactly the same electronegativity, like chlorine, then Cl2, no competition for the bond pair, it's down here. obvious. If I look at something which is here, let's say I'm going to take cesium and francium and fluorine, then these are as different as they can be. This has an electronegativity of 4, this of 0.7. A difference of 3.3 makes it 97% ionic. That means CSF is up here. If I look at aluminium and fluorine, AlF3, the difference in electronegativity between Al and F makes it about here. Oxygen is the second most electronegative element. So oxygen is a little bit different, a little bit less electronegative than fluorine. So what I'm doing is I'm saying, let's assume that they're covalent to start with. Is the electronegativity difference great enough for the chlorine or the oxygen to take the electrons away from the aluminium? And it's true for aluminium oxide, it's about there. All of the other compounds of aluminium, unless there is water, are not electronegative enough to make it that side of here. So aluminium chloride is here, aluminium bromide is here, aluminium iodide is here. So what we're doing is we're saying, okay, if I imagine that aluminium compounds are covalent to start with, here it is as covalent aluminium fluoride, it's not covalent, we know that. Then what happens, don't forget these ones, doesn't matter, okay? Then what happens here is that the difference between these two means that this pair of electrons, which should do this, actually just does this. And therefore this bond breaks, that bond breaks, and it becomes Al3 plus and F minus, okay? But if I have aluminium chloride, same idea. I say, okay, let's assume that they are covalent. The difference in electronegativity is great enough for this pair not to share equally, but to spend most of their time around the chlorine, but not enough for it to become Al3 plus and Cl minus. And therefore, although AlF3 and Al2O3 are that side, all of the other ones are this side. Does that help? So, to my mind, yeah, okay. To my mind, NO is a free radical. I have not seen a bonding picture question in any KCSE exam, and I did an analysis of 5 years. I have never seen the mass for the NO bonding in a dot and cross diagram. We'll show you. So the idea is, I think if you're teaching covalent bonding and ionic bonding, it is easier to teach it as covalent and ionic are separate. It is much more truthful to draw it like this. Much more truthful. Now, NO, when you think about it, O only has 2 electrons which it needs. So the dot and cross in NO has to look like this. Oxygen has 6 electrons to start with, 2 in there, 2 more out here. Nitrogen has 5, 1, 2, and if you look at this, we've got a problem. 1, 2, 3, 4, 5. Now the nitrogen is 1, 2, 3, 4, 5, 6, 7, not 8, and therefore it has to gain 1, and therefore it is a free radical. Now the nitrogen, it shouldn't exist, nitrogen monoxide, which is why nitrogen monoxide automatically, as soon as there's any oxygen around, I think I showed you nitrogen ammonia. Oh, no, sorry, not you, one of the classes. When ammonia decomposes to form nitrogen monoxide, it's white fumes, and almost immediately they turn brown, because nitrogen dioxide, nitrogen 4 oxide, can equal up the number of electrons. So in other words, we've got a problem because this there is not stable. As far as the nitrogen is concerned, the oxygen has become stable, 2, 4, 6, 8 electrons. The nitrogen, 2, 4, 6, 7 electrons. And therefore, this either has to pick up an electron to become NO minus, or that makes it a free radical, which is why nitrogen monoxide, nitrogen 2 oxide decomposes ozone in the ozone layer. Next question. Let me see in the chat, see if there's anything. How can I make chemistry a booster subject in my school? This is really difficult to tell. Most students have a mindset that moles is a difficult topic, however, come across as when students talk about something being difficult, I say most things which are worth doing are difficult. If you want to be a brilliant high jumper, you don't do it sitting talking about what you're going to do on Saturday. You do it by going out and jumping. If you want to do anything, you have to try. You can't do, I mean, Iestyn mentioned the 10 minutes, and that's really important. You know, if you don't spend 10 minutes doing something, you're not serious about it. Now, it is true that some things are more difficult, but for me, one of the best things I was ever told as a teacher, do not ever tell the students, now, we're going to do a difficult topic. Because automatically, some of them go, "Oof, I'm useless at chemistry, I can't, no, shut up, sir, la, 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 la." You know, it doesn't happen. I go, no, you can't tell me this, it's difficult, you know? So never tell them it's difficult. Maybe it is difficult. Maybe they go, hey, this is difficult. I go, is it? I always go, really? I thought you were clever. I must have explained it badly, you know? So I make it my fault, but I don't tell them it's difficult. I never tell them it's difficult. I tell them, sometimes I lie, sometimes I tell them it's easy, and another class has just done it really easy, and it's not true, but maybe it convinces them, maybe they think, yeah, we can do this, we can do this. And what I've said about the moles is if you structure the information well, they will get it. Next question, let me see. Nice lunch. I like the Kibera comment to everyone, nice lunch. I think that's good. That is probably the most positive thing I've heard all day. That's really good. Nice lunch. Very good. So I'm going to just see in the chat, see if there's anything else in the chat. Ooh, where's it gone? Chat. Anybody else want to put anything in the chat? Have not understood the last lesson redox. Yes, I could do that. Yes, you're absolutely right. If you were given some tablets, no, we don't want to teach your students. Somebody has said, I'm not sure who it is. Somebody has said a long time ago, has said, if we could teach your students. No, I don't want to teach your students. I think your students are fantastic. I think your students are harder working than my students, okay? But they should be taught by you because they need to see the role model is you. They need to see that you understand chemistry, physics, maths, and so on. They need to get the feeling that they can do it because you can do it. Look, they're just a bit older than me. Seriously, really, really important that they are not taught by somebody a long way away. It's really, yes, I can teach chemistry. So what? You can teach chemistry. You absolutely can teach chemistry. One of the best pieces of advice I was told about teaching was, as long as you are 1 page ahead of the kids, you are king. If you are 1 page ahead, like in the textbook, if you've got a textbook and you're going through the textbook, if you are 1 page ahead and you already know what is on the next page, you can tell them. You only have to be 1 page ahead. It takes many years, 39 years, 300 days, to be really confident about what I do. I will still get things wrong. It doesn't matter. I can learn again. I can go, sorry, kids. Every so often I get a calculation wrong. Every so often we have a calculation. I didn't read it properly. I do it. I get it wrong. Sorry. Anybody else got a question? Come on, have some courage. Turn on your microphone and ask me a question. I'm afraid I don't have any other experiment I could show you, which is a shame because it would be nice for those people who've been honest and stayed around to do some more. I will send this the two presentations and some others to the headmistress, and she can get them out to you or put them somewhere where you can get at them. But do please ask a question. I like answering questions. I love that purple jumper. I love that purple sweater. Kibera, I love that color. It is so good. That is the color of phenolphthalein in alkali. Oh, hang on, let me just. Why is it that CuCO3? Yeah, that is a good question. Okay.
Teacher Mark, one more question.
Yeah. I've just had one. I've just had one from Kibera. The question was, why is copper carbonate green and copper sulfate blue? Firstly, copper sulfate is not blue. Copper sulfate is gray unless it has water. When it has water, then it has d orbitals, and the d orbitals split, and the light interacts with the d orbitals, and it makes it blue. But the green-blue thing, copper chloride is green, copper nitrate is dark blue, copper sulfate is pale blue, copper hydroxide is really pale blue, copper carbonate is green. And so they're all very similar. And that is because when things are colored, it is because when light hits it, it promotes electrons to a higher level. And the gap between the lower level and the higher level is very similar in all copper compounds. But sometimes it's a bit greater and sometimes a bit smaller. So they are all bluey green, but they're not all the same. And it's about what else is attached to the copper. So we've got Cu2 plus is bluey greeny, but with chloride, it will be green, and with copper nitrate, it will be blue. Okay. Sorry, we have another question. Did we have another question in the chat, Headmistress? Please send us the slides as promised. Yeah, okay. Yes. Well, I tell you what, I will send them to. How can I get you on YouTube? Oh dear, I'm not. I will find my YouTube thing. I have done some lessons on YouTube, but I've been wondering whether to do more. I am thinking of putting small experiments onto YouTube, films of things like that, like the sugar, because sometimes it's difficult to see that. So we could do them little films, 2-3 minutes, where you could show a class. You could say, on YouTube, I can find this. So we could do that. That would be quite easy. If you had some experiments you want me to show you, I could do them and we could see them, because I'm very lucky with what I have in the laboratory here. Do we have any other questions? If not, I will probably say goodbye. And honestly, I wish I could come and teach with you. I wish I could come and work with you in your school, because we could have some fun. We could make your students smile and then shut up and do lots of work. This is the thing. You get them to do lots of work. Like you work hard. That's an admirable quality. Your students need to do more. Promise. You get them to do the work, they will fly. And I know that chemistry is more difficult for many people than physics or maths. I know it. And it's, Look, my yellow stuff from the beginning has settled. There is the lead iodide at the bottom. Okay, headmistress? Headmaster?
Thank you, Teacher Mark.
Thank you very much.
It's a pleasure. If any students have anything, they could leave it in the chat pane and I should be able to answer in the chat pane. I will be here for a few more minutes, but I will send the PowerPoints to you guys, okay?
All right, we will share with the teachers.
Okay.
Asante sana.
Asante Sana, back to you. Thank you for your
Can you
patience.
Yeah. Thank
Hey,
you.
Friday. Goodbye. Students, Matari, I really like you guys. Kibera, I really like you, and particularly that jumper. I want that jumper. Okay. Hello, I want the jumper. I want it. I'll send you the presentation if you send me the jumper. Okay. Otherwise, no presentation. Okay. All right. Should we close this, guys? Thanks, Mike. Thanks, Michael.
Take care.
Shall I finish it?
Yeah. Close it off.
I will.